Okay, so a couple different options for us to develop the derivative of an inverse function. And I'm going to go through both options with you, hopefully relatively quickly here. All right, so the first thing I'm looking for is the derivative of the inverse tangent function. Okay, so I can kind of use that summary chart idea, or I can use some implicit differentiation. I will show you both. Okay, so for this example, we're going to let f of x equal tan x, okay, and then the inverse function, which we'll call g of x just for the sake of ease here, is obviously going to have to be arc tan of x, because we know that those things are actually inverses. Okay, so what you can say then, we know what the derivative of f prime of x is. That's not a big deal, right? That's secant squared x. We've known that a long time. So then we would know that the derivative of the inverse function, right, has to be 1 over f prime of g of x, okay, which in our case looks like 1 over secant squared of arc tan x, okay, if I'm replacing g of x with the inverse function. Okay, here's where a little trickery comes in. There is a trig identity that says secant squared x is the same thing as tan squared x plus 1. Okay, and so if I want to replace this secant squared of this with tan squared of that plus 1, it could be tan squared of arctan x plus 1. That would be equivalent using that trig identity. Well, what do we know about tangent and arctangent is that they totally undo each other, and so what it means is that this must be the derivative of arctangent, okay? And so I could summarize it like this: the derivative of arctan x actually equals 1 over x squared plus 1. Okay? So that's fine as long as you know that trig identity. Okay? With implicit, it looks a little bit different. Okay? And so basically the question is, what is y prime if, basically, find y prime if y equals arctan x already. Right? What is the derivative of arctan? Okay, so the first thing that I would say then is if I want to, I could take the tangent of both sides. So it'd be like tan y equals tan of arctan of x, okay, which would be the same thing as tangent of y equals x. And one thing I know is that in a right triangle, right, the tangent of an angle equals the opposite over adjacent. And so I could think about this as being the side lengths of a right triangle, all right, where the angle is y, and so opposite would be x, and this would be 1. And then using Pythagorean theorem, right, I know that this missing side would have to be 1 squared plus x squared equals this missing side squared, and so this missing side would be the square root of 1 plus x squared, just from Pythagorean theorem. Okay, so then let's go ahead and do some implicit differentiation of this equation right here. So if I take the tangent of y, I want it to be secant squared y, and then I'm going to have y prime, and the derivative of x over 1 is just 1. So that's not a big deal for me to solve for y prime. Right, y prime equals 1 over secant squared of y. All right, well, I can use the triangle that I made, because this also has angle y, to put this in terms of x's if I want. Okay, so I know that from SOHCAHTOA, cosine of an angle, right, is adjacent over hypotenuse, which means that secant must be hypotenuse over adjacent. Okay. So if I look up at this triangle here then, secant y must be the same thing as the hypotenuse, the square root of 1 plus x squared, over the adjacent, which would be 1. but I'm not interested in secant y. I'm interested in secant squared y. And so if I square both of these things, that gets rid of the square root, right? And I basically have 1 plus x squared squared, or just 1 plus x squared. And so if I take that back down here, then I see that y prime must be 1 over 1 plus x squared, which is the same result I got the other time. So if I do the derivative of arctan x, that is the same thing as 1 over 1 plus x squared.